All right, guys, so in this section of the notes, what we're going to be looking at are some of the properties of exponential and logarithmic equations. In particular, we're going to look primarily at the properties of logarithmic equations, because really exponential equations, we should have already seen in Algebra 1, and in fact, we've already done some review of those actually as well. So before we get into a lot of those properties, which we'll see are very similar, let's go ahead and talk about the general inverse property of exponential and logarithmic functions. Now, we've already seen the inverse property for functions with e and natural log, but it turns out the same works also with our just regular log and exponential as well. So let's say you had log base b of b to the power of x. Then just like we had with natural log and e, this log base b of b is going to cancel, and that leaves you with just whatever the exponent is, in this case x. The same is true if you did it in reverse, so having b to the power of log base b of x. The same is true, that b and log base b are going to cancel. That leaves you with just the argument for your logarithm, which is just x. So what that does is it makes simplifying a lot easier if you are able to recognize that. And in addition to it, it allows us to also convert between the different forms of equations. Let's just talk about evaluating first, because this is probably the simpler part to look at the beginning. So for these examples, if we had 4 to the power of log base 4 of x, 4 and log base 4 cancel, and that just leaves you with 6. Next, for log base 2 of 2, again, log base 2 of 2 cancels, leaves you with just the exponent, which is 7. Or we might even have multiple expressions in the same part. And in that case, we do the same thing. Log base 4 of 4 cancels, 5 to the power of log base 5 cancels, and log base 2 of 2 cancels. And then when simplifying, negative 2 plus 8 minus 9 is negative 3. So they definitely make evaluating easy, but primarily what they're used for is to convert from one form to the other. So when we want to convert from one form to the other, we're just going to use the inverse operation on both sides of the equation. Again, we've talked about inverses. This is the inverse property. That's going to be how we'll convert from one form to the next. So let's say, for example, on number 1, we had 4 to the power of 3 is equal to 64. So notice that it's already in exponential form, and so as the hint, it even tells us that we're changing it to logarithmic form. So what we're going to do is we're going to take a log of each side, but we have to make sure that the base of the log is the same as the base of whatever your exponent is. In other words, we're going to take log base 4 of both sides of our equation. And when we do that, we're going to use the inverse property on the left side to say that log base 4 of 4 cancels, and that leaves us with 3 is equal to log base 4 of 64. On number 2, we'll do the same thing. We've got 64 is equal to 2 to the power of x. Here, the base of our exponent is 2, so we're going to take log base 2 of both sides of our equation. And when we do that, this time on the right side, you'll have log base 2 of 2, which will cancel. And that will leave you with the equation that log base 2 of 64 is equal to x. Finally, on number 3, we've got 5 to the nth power is equal to 3h. Here, the base of our exponent is 5, so we'll take log base 5 of both sides of our equation. And when we do so, on the left side this time, log base 5 of 5 will cancel. That leaves you with just the exponent, which was m, being equal to log base 5 of 3h. Now let's look at how to go the other direction. So maybe instead of going to logarithmic form, we are already in logarithmic form and want to change to exponential form. We're going to do a similar process. We're still going to use the inverse property, but now we have to use it a little bit differently. First, we're going to want to identify what is the base of our logarithm. So on number 1, log base 3 of 27 is equal to 3. That means that our base that we're going to want to use is 3. So what we're going to do is we're going to use 3 as the base of an exponent. In fact, we're going to take 3 to the power of both sides of our equation. So that's 3 to the power of log base 3 of 27 is equal to 3 to the power of 3. And so then our log base 3 of 3 cancels. That leaves us with just the exponent, which was 27, is equal to 3 to the third. And that should kind of make sense. In fact, if you take 3 to the third and type it into your calculator, you will in fact get 27. Next, let's go ahead and convert log base 5 of y is equal to b. So here our base is 5, so we're going to take 5 to the power of both sides of our equation. And so then on the left side, 5 and log base 5 will cancel. That leaves us with just y by itself is equal to 5 to the power of b. Finally, we've got log of z is equal to 3. And so it doesn't tell us what our base is, but remember when it's not written, we assume it's the common log. In other words, we assume that it's base 10. That means that 10 is going to be what we'll want to use as our base on both sides of the equation. So we'll take 10 to the power of log of z is equal to 10 to the power of 3. And then your 10 and your log base 10 is going to cancel. That leaves us with just z is equal to 10 to the power of 3. All right. So some more properties of logarithms. Let's go ahead and talk about these, and we'll kind of compare them to what they are for exponentials as well. So let's talk about the exponentials part first. So for the product property, with exponents, if you had something like x to the power of 2 multiplied with x to the power of 3, that was the same as taking x to the power of 2 plus 3, which is x to the power of 5. And so with logarithms, we're going to have a similar property. If we have log of a multiplied by b, then what we can do is we can actually separate those into the logarithm of a plus the logarithm of b. So when we're multiplying and we've got that common base, we still add together. This time we add the logs separately. And the same is true of any base. So whether it's the common log like we saw there, or whether it's the natural log, and again, it doesn't matter what your base is. You just make sure to use whatever that base is when you write down those logarithms. But again, multiplication is separated by addition. So to take a look at a couple examples, let's say you had log base 2 of 4 multiplied by 8. Then what we could do is we could separate that and write it as log base 2 of 4 plus log base 2 of 8. And again, we can simplify that. We're going to wait to simplify until later on when we look at expanding and condensing. So for right now, that's just how we're going to leave it. The same is true on number 2. So when we have log base 5 of 5 times 25, we can rewrite that as log base 5 of 5 plus log base 5 of 25. So again, when you're multiplying, you separate that using addition. All right. The next property we're going to look at is the quotient property. So if you remember what the quotient property looks like for exponents, it said that if you had something like x to the power of 7 over x to the power of 4, that you would subtract your exponents and say x to the power of 7 minus 4, which then you would simplify and just call x to the third. So with logarithms, the quotient property gets separated with subtraction. In other words, if you have the log of a over b, then we could separate that and write it as the log of a minus the log of b. And again, the same is true of natural log as well, or a log of any base. So the natural log of a over b, we could also write as the natural log of a minus the natural log of b. So to look at some examples, if we had log base 2 of 32 over 8, then we could also rewrite that as the log base 2 of 32 minus the log base 2 of 8. And then for number 2, for log base 3 of 9 over 27, we're going to rewrite that now as the log base 3 of 9 minus log base 3 of 27. All right. The next property that we're going to talk about is really the last property where we would compare the two side by side. And then we'll have a property that's somewhat unique to exponents and logs. So with the power property, if you remember what that looks like for exponents, if we had something like x to the power of a, well, let's just use a number, x to the power of 3 to the power of 4. Remember that we can rewrite that using multiplication as x to the power of 3 times 4, which is x to the power of 12. And to the power property really relates that to multiplication. Here's how that looks for logarithms. If we had log of a to the power of b, we can rewrite that as b multiplied by log of a. In other words, your exponent can be multiplied in front of the logarithm instead of being with the argument. Obviously, then the same is true of natural log, and for any log, if you had natural log of a to the power of b, you can rewrite that as b multiplied by the natural log of a. Okay, so in this next example, where we've got log base 2 of 8 to the power of 4, then what we could do with that property is rewrite it as 4 multiplied by log base 2 of 8. And on number 2, we could do something similar, where we've got log base 4 of 4x to the third. We could rewrite that as 3 multiplied by log base 4 of 4x. All right, the last property that we're going to talk about is really helpful in regards to our solving of equations, which we won't actually look at until next section, but it's an important property to look at right now as well. So what the one-to-one property says is that if you have log base a, or log of a rather, equal to log of b, then that implies that a has to equal b. In other words, if the two logarithms are the same, then the two arguments have to be the same as well. Obviously, the same is true of natural log, but let's go ahead and talk about exponents. If we had x to the power of a equal to x to the power of b, then this implies that your exponents have to equal each other, that a has to equal b. So let's look at how this would work with a couple examples. So for the first example, we've got e to the power of 5x equals e to the power of 10. Since our bases are the same, then what we can do is just look at the exponents and say that 5x has to equal 10, and then we could go ahead and solve that if we wanted to say that x is equal to 2. As for number 2, there was a typo in this problem, so if you can make sure to put parentheses around the 5x minus 3, we've got log of 12 is equal to log base 10 of 5x minus 3. And while at first the logarithms do not look the same, remember that when log is written without a base, we assume it's the common log, and we assume that it's base 10. So it turns out that they are in fact the same. And so then what we can do is we can just set the arguments equal to each other and say that 12 has to be equal to 5x minus 3. Which again, if you wanted to go ahead and continue solving, you could by adding over the 3 and then dividing by 5 to come up with x is equal to 3. And I think that would be a good spot for us to stop for this particular section and continue in a second video. So that at least gives you an idea of both the inverse property as well as all of the kind of more general properties of logarithms. In the next video for this section, what we're going to look at is how you can use those properties to either expand a logarithm or to condense a logarithm. Until then, have a good rest of your day.